Okay, today we start section 4.4. This is part 1. We'll be doing this in 3 parts because this is probably the most important section in the book. This is the fundamental theorem of calculus. The fundamental theorem of calculus, what I want you to understand in sort of intuitive terms, is this is a connection between our 2 major concepts in calculus, derivatives and integrals. And basically what the fundamental theorem of calculus says is the integral is related to the antiderivative. And we're going to see this in different forms. Today we're going to take a very algebraic computational approach, and then as we move through this section, we'll be looking at more conceptual type things. But it's very important we keep this in mind. We have limits, but limits are sort of the nuts and bolts behind derivatives and integrals. The 2 big ideas. This is the theorem that links those 2 big ideas and formalizes this idea that we treat them basically like inverse functions. And this is a connection I hope to make basically for the rest of the year. Okay? So let's do some examples here. Definitely want to get this down in notes. Basically the way we do any integral, integral of course being the area between f of x and the x-axis. If it's above the axis, positive. If it's below the axis, negative. You take the antiderivative of f, you plug in the top limit minus the bottom limit, and that works. So now we can find exact values without doing any of the approximation methods we've been doing all year. So let's get to it. Okay, so let's look at the examples. We'll start with 2. We're going to first do these without a calculator, and then we're actually going to use our calculator to check using the numerical integral feature in our calculator. This is something that we'll be using quite often in an open calculator context, but today I want you to check these values, okay? So let's go ahead and take a look here. So the first thing you want to do with any of these is find the antiderivative. So the antiderivative of 1 is x minus, and then the antiderivative of this is, we'll raise that to power, have a 1/4 in front. Now, always the right antiderivative. Now, in this case, we don't need the plus c, and I'll explain why in a moment. But when we're doing definite integrals, so definite integrals just means we have the numbers. It means we're talking about the area between f of x and the x-axis. Above the axis will be positive, below the axis will be negative. We don't need the plus c. We only need that when the numbers aren't there with the indefinite interval. So we'll put the 1 here, 2 here. So the first thing we do is we plug the 2 into both of these. So this will be 2 minus 1/4, 2 to the 4th, minus, and then we'll plug the 1 in. The big thing here is make sure this goes in parentheses because we're subtracting this whole thing. So 1 goes in, 1 minus 1/4, and then 1 to the 4th. So take the antiderivative. By the way, you have to show your antiderivative here. And this is something that if you don't have, even if you have the correct answer, you'll definitely lose points. So you plug in the top limit first, and then the bottom limit. Okay, so let's calculate this now. This will be 2 minus, this will be 16, 2 to the 4th is 16 over 4. I know that's 4, but let me point out at some point I'm going to have to deal with that fraction, so I'll leave it in the form of 16 over 4. Minus 1, I'm just doing this negative, plus, and then this will be 1/4, okay? So as I talked about, that's why I left it like this. So now what we see is we're going to have 2 minus 1, that's equal to 1. And then negative 16 over 4, so that's going to be plus 1 over 4, so that'll be minus 15 over 4. So now at this point, 1, I want a common denominator, so call 1 4 over 4. So we get 4 minus 15, and that is negative 11 over 4. Okay, now we want to check this using our calculator, and I encourage you to work along with this. So what we're going to do is, and it really depends what calculator you have. If you have the newer version, it's pretty self-explanatory. You go ahead and go math, and you go down to 9. This shows up as n-deriv, okay? And math 9, whether you have a newer calculator or an older calculator, that's what you're going to hit, as long as we're talking about a TI calculator, Texas Instruments. If you have a different calculator, I'm sure it has these features. It's just you're going to have to look that up in the catalog. Okay, now if you have a newer calculator, you'll get a form that basically looks like this. And so all you have to do in this is you plug in obviously the values and the function, and then actually it has like a blank here, plug in x there. So let's go ahead and do that. and we get negative 2.75, which of course is the same thing as negative 11/4. So I definitely want to do those checks, and I encourage you to do these, if not on all of them, quite a few of them, because we do want to see that we're doing these correctly. Now, I will tell you, if you have an older calculator, like I think like the TI-83 Plus, you're not going to get that nice notation, but it's not too bad. This n deriv, excuse me, it's not n deriv, it's the numerical integral. I think it's an int. It shows like parentheses, and the way you enter this is you enter your function. Oops. So we'll enter the 1 minus x to the third, comma x, comma your bottom limit, and then comma your top limit. And this will do the same thing for you. So those of you with the older calculators, you just have to know to enter it like this. Okay, and I think that's the, let me double check this. So math 9, oh, sorry, math, yeah, actually it's fn in for, I think that's finite interval. All right, so let's move on to problem 2. Before I take the antiderivative of this one, I do have to rewrite it, so I want to rewrite this one. So I'm going to call this integral from 1 to 9 of x to the negative 1/2 dx. Okay, so raise that a power, that'll be x to the 1/2. Put a 2 in front to cancel, and now I'm going to bracket this off. Now, one thing about these, I can keep any constant out front, which will make life maybe a little bit easier. This one is not a big deal. But if we keep that constant out front, then we can distribute when we're done, okay? So we plug 9 in first. That would be x to the 1/2, obviously means square root. So square root of 9 minus square root of 1. Square root of 9 is 3, minus square root of 1 is 2. 2 times 2 is equal to 4. And then once again, let's check this real quick. So math 9, let's plug in the 1 to 9. And then x to the negative 1/2. And there you go, we see that that's correct. Okay, let's go ahead and go through a few more examples. Okay, so I have 2 more examples today, and that will be it for this video. Like I said, very computational today. We're kind of taking this, because this is such an important idea, we're taking this in sort of little nice bite-sized pieces. So let's go ahead and take a look at this one. So we're going to take the antiderivative of cosine, negative sine. Now keep in mind that when we take the antiderivative of sine, we actually get negative cosine, but we already have a negative in front of there. So that's just going to be cosine, positive cosine x. And the one thing I'd encourage you to do, especially as we're starting off, is take your derivative of cosine x and check to make sure that that is correct. So if we take the derivative of cosine x, we get negative sine x, and that is what we see up there. So we're going to evaluate that from pi to 2 pi. Okay, so we plug in the 2 pi, so cosine of 2 pi minus cosine of pi. All right, and cosine of pi is, let's see, cosine of pi, so we're over here, so that's 1, 0, so that's 1. Minus, and then pi, that's negative 1, 0, so that's minus negative 1. So 1 minus negative 1 is equal to 2, and there you go. I encourage you to check that. If you do check this one, make sure you're in radian mode. Okay, 4, we have to remember this, normally when we have some sort of term in the denominator, we would write that with a negative exponent. If you do that here, just keep in mind, if I raise that a power, I end up with 0. So that should indicate that this is not going to work. This is the only one that doesn't work with reverse power rule. So as soon as I see that degree 1 thing in the denominator, this is going to be ln and the absolute value of x. So that's our antiderivative here, and we're evaluating that from e to the third. Okay, so we plug in e to the third first. E to the third is positive, so we don't have to worry about the absolute value anymore, and then ln of e. And now keep in mind, when we do have these logs, you're always asking yourself, what do I raise this base to get this? So what do I raise e to get e to the third? Well, that's clearly 3 minus, what do I raise e to get e? And of course, that would be 1. And there we go, we get 2. And then once again, give that a check and make sure that that is correct. So that is our video 4.4 part 1, the fundamental theorem of calculus. Yeah, and like I said, we're going to be moving through this section in a few more videos.